real treat for our first talk today. This is going to be a live talk from Hawaii. The Resolve campaign is ongoing. This is a multi-center effort involving Ames. Jen Heldman, who all of you saw earlier, and who's sitting in the back of the room here right now, is involved in this in the control room at Ames. KSC is involved, JSC is involved, and I suspect others as well. So it is a real pleasure to introduce my friends Jerry Sanders and Bill Larson, who are going to talk on the Resolve Lunar Rover Field Campaign live from Hawaii. Jerry, go ahead. Jerry, are you on?
Slight operator error here on my part.
No problem.
Can you all hear me?
Yeah, we can hear you. Thanks.
Great. I want to thank you for giving us the opportunity to actually present what's going on. Normally, we have the opportunity of presenting results after accomplishments have been completed, but we're actually still in the middle of analog testing. And so I'd like to give an overview of what we've been doing here, and hopefully spur some thoughts at the conference that we weren't able to attend. So let me see, I changed the charts here, but if they don't seem to be showing up,
We got them.
oh, there we go. So to step back just a little bit to explain what we're doing here, basically we've been working on the idea of using space resources for future robotic and human exploration activities. And that pretty much involves trying to use those resources for different reasons. And it can change how we explore space. So to begin with, it helps us potentially reduce mass, the number of launch vehicles and such, which then equates to cutting the cost of these robotic and human missions. And leading to the idea of potentially even reducing the risk and increasing the flexibility by making things there, whether it's propellant, life support, gas, radiation shielding, or whatever, instead of having to bring it from Earth, or if something fails, you don't have to wait 2 years for a supply ship coming from Earth. The long-term goal is to enable extended human presence as well as space commercialization using these resources off planet and potentially coming to Earth. It looks like it's going to take several seconds to change charts, so I'll try to anticipate that. What we know about the moon, obviously there's a lot of people there that are discussing volatiles, and what's been learned over the last several years with the Lunar Prospector, Chandrayaan, and especially L-Cross. And what we basically are aiming towards here in Hawaii is a combination of, first, what are the polar volatiles and performing ground truth, as well as other volatiles and minerals that may exist on the moon. From L-Cross, and this is the chart I received from Tony Polifree, not only do we see the potential for large amounts of water, but other interesting consumables such as hydrogen itself, ammonia, and carbon monoxide and small hydrocarbons. And the combination of all of these volatiles really can be game-changing with respect to how we explore the moon. So what's the next step from L-Cross? It's basically trying to get a ground truth. Not just what are the volatiles that are there, but how deep are they, how widespread, and especially how much energy is required to extract those resources. So over the last several years, we've been working with the terrestrial mining, terrestrial technologies and processes, and convert those into what we might do to insert ISRD into future exploration. And the mining cycle on Earth, as well as what we're looking at space, starts with the global resource identification from spacecraft such as LRO. We then go and specifically go to areas of high interest, like the polar regions, to provide that ground truth. And with that data, we eventually will hopefully start mining and processing those resources for subsequent use, for, in particular, power, propulsion, flight support, etc. And the first critical step in this mining cycle is really understanding and prospecting at that local resource location.
There we go. Okay, so the reason why we're out here in Hawaii for the analog field test is we have three major objectives. Overall, the focus has been to examine that first step in the space mining cycle, which is to prospect. So the first objective is to demonstrate integrated mobility, platform, science, and payloads for a lunar polar ice volatile mission. The second objective deals with the Space Mission Directorate MAMA instruments, and that is to demonstrate science instruments and operations associated with a terrain and resource site characterization before a crew would arrive. And the third objective is to actually demonstrate mission support and operations for robotic precursors. In particular, we're looking at a very short mission on the moon at a polar location for 5 to 7 days with limited power and communications capabilities. So we would be operating 24/7 literally if we perform that mission. And one of our objectives is to learn that process. Okay, so the next chart. Just a brief background. We're actually testing at 2 locations here on Mauna Kea. The resolve activity is occurring on your bottom left hand in a valley cinder area called Puhūhai Wahine. At the same time, we are testing the MAMA science instruments up at the Apollo Valley, approximately 12,000 feet up. And most of the people that are performing the analog field test are staying at Halipuhaku facilities where we have dormitories and cafeterias and such.
Ricky, have we lost them again?
It appears we've lost them again.
Yeah. Jen, would you be? Yeah. So I asked Jen Heldman earlier. Jen is intimately familiar with the Resolve project. She's been working it this week. She's not familiar with Jerry's charts, but she does know a lot about the project, so she's agreed to talk to it. And if we get Jerry back.
Pipe him back in.
Yeah, thank you very much.
So I can check for the slide?
Yes, and do it just by pointing in that direction.
Okay. All right, sure. Well, thanks. I haven't seen these slides, so it'll be fun for all of us. So as Jerry mentioned, we are in the middle of doing this Resolve field campaign. And just as a little background, my involvement here, we have the science backroom here at Ames. So I've been splitting my time between the forum and then working in the science backroom. There's also a flight operations mission control out in Hawaii, and that's where a majority of the people are on site working on the rovers, working with the instruments and all of that. So it is a very long acronym, Regolith. I'm not going to try and make it up. It has to do with regolith, excavations, science, volatile analysis, right, on the moon. And the idea is to do this in situ resource utilization. And the goal right now in Hawaii for Resolve, well, maybe we'll get to that. Let me just see what the next slide is. Oh, this is where they are. So what we're doing is using this rover to do prospecting. And the whole idea is to use this as an analog for what we would do on the moon. I'm following up on the LRO results, on the LCROSS results, because the next step, we think, would really be to do some ground truthing on the ground, obviously, with a rover to really do some more localized characterization of hotspots. So what we'd like to do is get some more detailed information on the distribution and characterize these hydrogen hotspots, and that's what we're doing here. And in how this field campaign is working is we have the rover with 2 prospecting instruments on it. There's a neutron spectrometer on board, and there's also a near-infrared spectrometer. The near-infrared spectrometer tells us about the surface volatiles. We watch that data coming back in real time. The neutron spectrometer tells us about the upper meter or so we can get some idea of the subsurface volatiles. And basically, we drive this rover on pre-planned traverses that we have planned, that the AIM science backroom has actually planned, since we're not on site, so we don't have that knowledge of boots on the ground. Plan out these traverses to areas that look interesting, and then we all watch the data coming back from the rover in real time, and we make real-time decisions based on if we see a hotspot, then we call an all-stop, that rover stops. We enter into a hotspot localization routine where we characterize what that hotspot, the extent of what that looks like, and then we make a real-time decision. Do we stop here, and do we want to take a sample? Do we want to auger down and see what's happening in the subsurface? When we auger, we just bring the tailings pile up, look at it with the near-infrared spectrometer to see if we see any hydrogen signatures, water perhaps, and or we can also take a core. We can take a 1-meter core. There's a drill on the rover that we're also testing out, and take a core, and then take that into the Resolve payload itself. Has a GCMS and a bunch of other instrumentation on it to do the volatile extraction and do further characterization of what's happening in that upper meter. So that's the essence of what's happening. Oh. All right, I'm not going to look at that because that would mess me up. So these are the 2 different sites. As Jerry mentioned, there's a bunch of MAMA instrument testing going on. MAMA is the Moon-Mars Analog Mission Activities Program. It's a ROSES element that you can apply for. And they're doing some instrument testing up in Apollo Valley. And then the Resolve rover is down here in Pu'uhaiwahine, and that's where we've been driving around. And the test site on Hawaii, very much like the moon. Obviously, this is one of the reasons why this site was selected. There are distributions of rocks. There's topography, which we're trying to deal with as well. There's not a lot of vegetation, and so the idea is to do the most realistic simulation that we can. And here are some images of Apollo Valley. I've never been there, but it looks very nice. This is where the MAMA testing is happening, and Apollo Valley is at a higher elevation further up. I might have already covered a lot of this. I guess I'm not going to read all of these slides. Presumably you can look at them. You can look at them later. But this just summarizes a lot of what we've already said. So we're talking about, as an analog for a polar mission, landing based on the following criteria: looking to Earth for calm, sunlight for the duration of the mission. So that's an interesting point. We heard a little bit about this in the last talk, is that you don't necessarily have to go into regions of permanent shadow to find the volatiles. And in fact, it's very difficult to operate a mission in permanent shadow with the complete darkness and the extremely cold temperatures. And we've been doing a lot of site selection work and looking at the data coming back from LRO and primarily, and some of the modeling that's gone along with that. And there are regions near the poles of the moon where you get on the order of 7 to 10 days of sunlight per month. And that's actually enough to keep you at very cold temperatures, just a few centimeters below the surface. And so you're at cold enough temperatures just below the surface where you can still sequester those volatiles. And that's maybe what's going on there, is that you can still have volatiles even in regions that get a little bit of sunlight. And so the idea for this mission that's being tested is that's the type of place you'd want to go on the moon. So you can do your rover operations in 7 to 10 days, and that's why you're doing this 24-hour mission ops that Jerry was mentioning, because you use that whole time in sunlight, do your prospecting, do your roving, extract your samples, do your analysis. So this may be a good way to get around having to go into the permanent shadow to do further characterization. And for the mission simulation, right, we're doing the mission ops, we're testing hardware, and demonstrating the full integration. So this is a full up sim, physical data, power, command, all of this is being tested now. Demonstrating the integrated operations of Resolve, the hardware and the software. So we go through the roving or prospecting phase, where we're looking at the real-time near-infrared and neutron data. We go through the drilling and the sample transfer phase, when we just find a hot spot and we decide to actually do the coring or do the drilling. And then the sample processing phase, where we use that Resolve payload to actually do the volatile extraction. We're doing all the mission operations on very strict timelines to validate this short duration lunar mission. So this is that 7 to 10 day constraint that we're working underneath. And demonstrate mission command and control with lunar time delays and bandwidth limitations. So that has all been worked into the mission ops that we're doing. Oh, so these are our objectives. Actually, I know this chart well because we have this posted up because these are the things that we are aiming to achieve during this field simulation. We want to demonstrate we can travel at least 100 meters on the lunar surface because we want to get some idea of the horizontal distribution of these volatiles. So when we're planning out our traverses and doing our ops, we keep that in mind. We wanted to make sure we did at least one coring operation so we can demonstrate the drill and the sample handling, and we can fit that in. Perform at least one water droplet demo. That's part of the Resolve payload where they're doing the volatile extraction. And then these are Cat 3 and Cat 4 are very nice to have, desirable things. I maybe might not run through those because I think we're getting close to the end. But suffice it to say, we're actually achieving our objectives. Here's a nice schematic of the rover itself. And you can see that there are a bunch of different instruments on there. So this is a joint project. We have the CSA, the Canadian Space Agency, which has been contributing a substantial amount of hardware. So you can see the auger and the core drill for the sample collection. The near-infrared spectrometer and the neutron spectrometer. So that is for when we're in the roving mode. So we do this prospecting and map out the horizontal distribution. And then there's lava and oven, which are two of the Resolve payload elements for the volatile extraction processes that are going on. And then operations control, the avionics joint between the CSA and NASA. It's big enough. I don't remember the exact dimension. Yeah, I don't remember, but it's person-sized. It's about as tall as this podium and a little bit wider. So here are some nice screen captures of the traverses that we've done. So these are the planned traverses that we made ahead of time. This is in the valley. In our first phase, we wanted to do these this is where the lander originally started, and we wanted to do these 3 pedals to fulfill our 100-meter traverse requirement. And then we are looking at the topography in here and also some of the features. There's some nice slope streaks that we wanted to look at. There are some nice flow features coming in over here we wanted to look at. There's some high albedo features down in here. So we were trying, using the remote sensing data, to target the most interesting places to go. And then in real time, we can follow where the rover's going. And you can see there's the tracks of where we actually went. And the ground data system that we have, the XGDS system, they developed it here at Ames, and it's been used in a lot of different field campaigns, Desert Rats, Pavilion Lake, NEMO, Resolve now. And it's really great because we can, in real time, track where the rover's going. We can tie the data to the location of where that data was taken. We can take notes. There's an interesting place here. And so it's a nice way to bookkeep everything that's been going on and keep all our data together. This is a schematic of the operations center as they are out in Hawaii with all the different console positions. And here's a picture of them actually working and somebody checking their iPhone. So here are some pictures of the rover itself. So here's a person for scale, Brad. Yep. So this is egressing from the lander. Here is the rover there outside searching around. Here is an example of one of the hotspot localizations that we did. So in XGDS, that ground data system software, we actually have data raster mapping where this color in here is the neutron signature. So basically where you get reds and yellows, you have a high hydrogen signal. And so when we see those, we do a hotspot localization to try and cover more ground around that area. And that's what you're seeing here. That's why there's a big blob of blues and reds and yellows. Here's a close-up of the actual rover with the instruments on it. So here's the NS, the neutron spectrometer, the near-infrared looking straight down, and then there's the auger. This was actually during one of the auger tests we did just yesterday, actually, is from this image. And you can see you have a cuttings pile. This is the drill operations camera, so we can see what's going on. There's the auger in there, and there's our pile that we're looking at with the spectrometer. Do you want me to keep going, or?
Well, yeah.
Since I put the schedule together, I know that I'm 2 minutes over.
That's okay. Why don't you keep going? Yeah.
Okay. I have no idea how many more slides there are, so.
5 minutes.
Okay. Here's objective 2, what we're also doing, testing the science operations and architecture so that we can get through this mission on the short duration timescale that you can. That's one of the things that we're testing is having a back room located not on site to help support the operations and the instrument operators that are out in Hawaii. And also, to their credit, to the team that's putting this project together, keeping in mind the science and how that plays into the exploration goals. And so it's really important when we get geologic context and things like that, and they're very amenable to us actually doing the science and collecting the science data, even when that impacts the timeline of the scheduling. We have multiple days of field operations. Yeah, I'm going to just skip through all these words. Maybe. Okay. So there's also a lot of instrument testing. These instruments are part of the MAMA testing that's going on up in Apollo Valley. They have another rover that's up there, and they're doing a separate field test, GPR, Mossbauer X-ray, the mesh system, the vapor system, et cetera. And so these are all funded separately, but it's a joint activity looking at different instrumentation that we could possibly use for doing lunar reconnaissance. And this is Apollo Valley. This is where the MAMA work is being done. This looks like 3 or 5 of their actual field site tests. I haven't been as involved in the MAMA work. We've been doing the Resolve backroom. And it looks like they've been doing some roving. And so it looks like they've been very successful. Okay. And here are some images of them actually doing the testing with those instruments. And they have a science operations center there as well. And so, yes, they have a separate rover that they're using because they're doing this testing simultaneously. Okay. Mission support and operations for Lunar Robotic Precursor, since that's the gist of what this whole entire field test is all about, is to lead up to a mission. And so when decisions are made as to what we should do, we're trying to make decisions based on what are the most relevant instrumentation that we could use, what are the things that we need to do to help raise the TRL level and bring these instruments and concepts up into flight readiness. So we're doing things like controlling and limiting the bandwidth. Obviously, we could be more productive and cover more ground to get more data back if we didn't have these types of constraints, but that's not what we're trying to do. We're trying to do this in the most realistic way that we actually can. We're doing remote operations from CSA, from the Canadian Space Agency headquarters, from NASA. So we're working with a lot of folks at JSC who have shuttle and ISS experience, and it's been really great for me working with them because if anyone knows how to do mission operations, it's them. And it's fantastic to have people that actually do this for a living helping us out. We're using the SNRF communication architecture. I forget what SNRF stands for, but it's very important. It's the way that we securely get all of our data and all of our mission operations information passed between all of the mission ops rooms, the back rooms, and then ultimately to the rovers. And then we're using the ISS and MSL planning tools such as SCORE and Playbook. So SCORE and Playbook are basically one and the same, but they're the timeline tools. This is how we keep track of all the different activities that are happening and all the different instruments and all the different locations and make sure that we stay on timeline. So there's a group that is dedicated to doing that, and it's very important because we're on this strict timeline for this mission simulation. Okay, so I think that that's it, and
thank you so much.
sure.
Can we have a huge round of applause